Good afternoon, everyone. Thanks for joining me today. My name is Dustin Douglas, and I am the Region Engineer for Geopier Foundation Company, covering the states of Texas and Louisiana. Geopier has been around for over 20 years, offering foundation support experience and ground improvement expertise. We've completed more than 10,000 projects to date, projects in over 48 states and over 25 countries. We're made up of a design-build team. Our submittals are designed by in-house PEs. Everything is backed by our E&O, and we have local installers that actually install the piers in the field. A little background on how Geopier came to be. So historically, there's been basically two options for foundation support, shallow and deep. If you had good soil, you can bear the footings right on that soil. Have marginal soil, maybe you got to remove some of it and replace it with engineered fill. And if you have really bad soil, perhaps you have to use deep foundations to extend down into better strata below. Well, in the early 90s, Geopier introduced a third choice, and they deemed it the intermediate foundation solution. And it works in all kinds of soils, And with time, the Geopier rammed aggregate pier system has gained popularity not only because of the upfront cost, but also because of how fast it is in construction. Geopier has many systems and applications to tackle all kinds of soil profiles. This current slide shows the different systems we have that can be implemented in more sandy and silty sandy soil profiles. And we'll be talking more about the impact system in particular as the presentation goes along. This slide shows the different systems we have that can be used and implemented in more cohesive and clay type soils. Also to the far right, you'll see kind of our bread and butter system there, our GP3. We call that our drill and fill, and we'll be talking more about that system as the presentation goes along. As mentioned previously, there are multiple ways to deliver Geopier rammed aggregate pier systems. But the three we're going to mainly talk about today are the GP3 system, the impact system that utilizes a displacement approach, and our X1 system, which is kind of like a hybrid system for us. For Geopier GP3, or our drill and fill system, we start by excavating a cavity. Then we add in some open graded stone and tamp the bottom bulb to kind of get the pier seated. And then we add in a well-graded stone and tamp it in 1 to 2 foot lifts up the shaft up to bottom of footing elevation. This slide contains a picture that shows the equipment that makes up GP3 construction. We use a Geopier drill and then a Geopier tamper to ram in the aggregate, and of course a skid steer to move the aggregate around on site and dump it into the hole. It's a very mobile crew. Generally 4 people can run it with 3 machines. We can install these piers very quickly. It says 30 to 50 piers per day right there, but I've seen them go in excess of 70 to 80 piers a day. And then it's a safe, clean, dry process. There's no water jetting or anything like that required. Here's a quick animation that can show the GP3 installation process. We drill the cavity, pour in the clean stone to make the bottom bulb, and then come up the shaft in 1 to 2 foot dense lifts. Rinse and repeat all the way up to bottom of footing elevation. The impact system utilizes a displacement approach to installation, and it consists of a high impact frequency hammer, a hopper, and a hollow mandrel. For impact construction, we first drive the mandrel to full depth, and then, as it is raised, flow stone down from the hopper through the mandrel. After driving to full depth, the mandrel is raised 3 feet and then driven back down 2 feet. And what you get are dense 1 to 2 foot lifts of aggregate. In the bottom left-hand corner of the slide, you can see the ring of chains that when the mandrel is engaged, bunched together, forming a compaction surface that is used to ram the aggregate into the soil. As mentioned, the impact system is a displacement approach. We can achieve depths of up to 45 feet. Like the GP3 system, it's a dry process, so there's no water jetting. Another great benefit of the impact system is that there are no spoils. So on contaminated sites, for instance, maybe a refinery site, you're not going to generate any spoils. Very fast installation, 40 to 100 piers per day. The X1 system uses a vertical ramming process, which is a combination of both replacement and displacement methods. And it allows for some flexibility in construction with the ability to build through caving zones that can sometimes be encountered during drilling operations. The slide also illustrates the different pier diameters that you'll see for X1, although the 18-inch is definitely the most common, and we are more and more getting smaller diameter piers as we continue to develop new systems and more efficient processes. This slide illustrates what installed geopiers look like in the field once the general contractor comes and excavates and forms the footings. And the beauty of geopiers is that you can place the footing steel and pour the concrete directly on top of the geopier elements. There's no pier cap needed. The direct results of geopier construction is an increase in lateral pressure along the shaft, which increases the frictional shear resistance. And soil reinforcement means there's no setup time for piers. So once we've installed the geopiers, footings can be immediately placed. This slide basically just illustrates that when you increase the lateral stress with the introduction of geopiers, you decrease the matrix soil's ability to compress via consolidation. The geopier approach is to improve soil where it's most needed. We do this by creating an engineered crust. We increase the composite shear strength bearing pressure and utilize two-layer settlement analysis with the upper zone and the lower zone. Total settlement is equal to the upper zone settlement plus the lower zone settlement. For the upper zone, we use a spring method or a modulus approach, and for the lower zone, we use conventional. And the total is a function, of course, of the width of the footing. Now let's talk a little bit about stabilization of slopes, embankments, and walls. We'll start with slope stability. Slopes and embankments fail when the foundation materials aren't strong enough to resist shear caused by new fill. In most of these cases, shearing occurs on a circular surface. The installation of geopiers will increase the shear strength of the foundation soils and increase the factor of safety. The aggregate in a geopier has a very high friction angle and a zero cohesion intercept. The composite shear strength of geopier reinforced soil is expressed as follows. We now have a weighted average of matrix soil and geopier shear strengths and the composite shear strength parameters. The shear strength is stronger because of the high friction angle in the aggregate. This slide contains an example calculation for reference. So what's missing? What still needs to be considered? The stress concentration to the stiffer geopier elements. As shown in this slide, the higher stresses are going to attract to the stiffer geopier elements, thereby reducing the stress acting on the less stiff matrix soils. By including the stress concentration to the stiffer geopier elements, we can calculate the composite values. typical R sub S factor for stability is normally 1 to 5 for flexible structures. And as we can see from the table on this slide, slope stability parameter values improve when geopiers are added. Slope stability calculations are performed using the composite shearing strengths for the geopier reinforced layers. For global stability, geopiers offer a high friction angle, an increase in composite shear resistance, and they increase global stability and slope stability. Now let's take a few moments to discuss an example. This was a project we performed in Krotz Springs, Louisiana for the US 71 slope stabilization project. For the US 71 slope stabilization project, we were tasked with looking at an existing roadway, US 71 at BDG Crossing. It was new construction, had added fill to the embankment and a new bridge structure, and the placement of this new fill had caused instability. This slide illustrates some of the severity of that continued movement after the torrential rains. We also noted longitudinal cracking in the roadway. Toe scarps were identified, and you can see those in these pictures here. This slide shows the extent of instability along that embankment slope. And I just love this slide. This was clearly before the panoramic functions we now have on our iPhones. Here's another view of the extent of instability along the embankment slope looking north. This was the boring location plan, and in red there you can see the scarp location. The soil conditions consisted of clay fill in the top, 10 to 15 or so feet, underlain by a lean clay and fat clay stratum. And the interface of clay fill and lean clay and fat clay on B1 was pretty close to the groundwater level elevation. Inclinometer data showed that the downslope area instability was about 10 foot, and the upslope instability was about 20 foot. And of course, this was one of those projects where we had the benefit of inclinometer data. Oftentimes, that's something we wish we had, but we don't always get on slope stability projects. So we ran our slope stability analysis and back calculated for the unreinforced condition, modified strength parameter values to arrive at a factor of safety equal to 1, and modeled it with the clay layer, upper clay layer, and the bottom clay layer. Added geopiers into the model to arrive at a factor of safety greater than 1.3. Actually, on this model, it was actually a factor of safety greater than 1.5. This slide shows how the geopiers were laid out in the zone. Each one of those little circles within that rammed aggregate pier zone represents an individual geopier running alongside US 71 in the embankment. This slide illustrates the cross-section of the geopier reinforced zone. And you can see the piers extend through the shear plane. I've also gone ahead and included some photos taken out at the site, just so you can kind of see what the operation looked like. So on this job, we also provided some post-reinforcement inclinometer monitoring to kind of just prove our design and make sure everything was sound after the geopiers were installed. And as you can see, both on the downslope and the upslope, the two tables there, or graphs there, there was no movement 3 months after construction. So in summary, for the US 71 job, we installed 340 Geopier elements to depths of 20 feet. We reinforced the slope and stabilized movement, and inclinometers show no long-term movement of the reinforced zone after the fact. Now let's look a little at the support of embankment and wall applications. This project was the Central Corridor railroad grade separation. Got the design team listed there. We were working with the city of Wichita on this project. Here's another project example, the Sienna Parkway MSC wall in Missouri City, Texas. We supported a 31-foot tall MSC wall on Sienna Parkway. Geopiers were installed at 7 feet on center, and ultimately 490 geopiers were installed in less than 3 weeks. So this project was good on the value side in terms of construction schedule. Got those installed pretty quickly. One more project here, the Picardy Avenue MSC wall. This was in Baton Rouge, Louisiana. We offered a Geopier solution using our drill and fill system, the GP3. Of course, you can see in the bottom right, kind of the pier layout, underneath the wall. The Picardy Avenue wall was 37 feet tall, MSC wall. Soil was soft to stiff clay. Geopier elements were spaced at 5 1/4 to 8 feet on center, and we performed the work on multiple phases. And now let's talk a little bit about tank foundation support. So for tank foundation support, we use the following design considerations. Bearing capacity, specifically edge stability, total settlement, and then differential settlement, center to edge and also perimeter. So when it comes to tanks and bearing capacity, if a tank is planned for construction on soft soil, there may be issues with the bearing capacity, as it is typically controlled by edge instability. So for bearing capacity, it's controlled by the edge instability. With a flexible steel floor, the tank doesn't act as a rigid body. So the tank floor is not rigid, and a slip surface is valid for rigid footings. The edge shearing mode of bearing capacity instability is most effectively analyzed using slope stability approaches. Geopier elements increase the composite shear strength of the foundation soils. They're installed to intersect the critical shearing surfaces. Geopiers are placed under the floor of the tank to take advantage of increased overburden pressure. And you can always go back to the slopes and embankments portion for determining the composite shear strength of Geopier reinforced soils. Geopiers typically increase edge stability factors of safety to greater than or equal to 1.3 for steel storage tanks. And we can verify our design with a modulus load test and also during hydro testing of the tanks. Now let's consider total settlement and differential settlement. For settlement control of the lower zone, these lower zone settlements that occur for pile-supported tanks are also large because of the same influence below the depths of the pile tips. Geopier elements significantly reduce the differential settlements along the tank perimeter because of an increase in uniformity in the upper zone soils. We also require a granular pad which transfers the tank loads to the top of the Geopier elements. And there's an equation there for the recommended thickness where S is equal to the spacing of the Geopier elements. Let's look at a case history here. This was a Houston fuel oil terminal project. It was the Area 14 tank farm, and the scope consisted of 10 new above-ground storage tanks. The project was located pretty much in the Brownwood area of Houston. The new tanks were 100 foot in diameter and 56 feet tall, and they had an 86,000 barrel capacity, so some pretty heavy loads. The subsurface conditions at the site consisted of variable clay fill in the top 15 feet, underlain by clay and sandy clay material below. Bearing capacity, edge stability was a concern in the variable clay fill material. And we were also analyzing the settlement in that variable clay fill as well. We utilized granular pads over the Geopier reinforced zones, and you can kind of see in this illustration kind of the typical design approach with just the Geopiers underneath the entire tank bottom. Another case history here, a couple of them really, two-phase, 2011 and 2012. It was Magellan terminals. One was in Galena Park and one was in a East Houston facility. For Galena Park, we were looking at tanks 419 through 428, and they were really good sized tanks, 120 feet in diameter. And then for the East Houston facility, we were looking at tanks 2505 and 2507, and they were even bigger, 188.5 feet in diameter. For the 10 120-foot diameter tanks at the Galena Park site, there had been some existing tanks that had been removed, and so we had to take that into account in our design. And ultimately, our design consisted of about 3,000 Geopiers, 30-inch diameter. We spaced them 6 to 6.5 feet on center with 14 to 18-foot depths. So we were able to tag into that stiff clay. For the Galena Park site tanks, our design did consist of supporting the entire footprint. As you can see on the right-hand side of the slide there, the layout. And the design criteria was 4-inch hydro center, 2-inch hydro edge, and then plus 2 inches post-hydro. That, of course, is settlement. So a nice decrease in the total settlement that they would have seen. I'm going to go ahead and move on from tanks and cover a couple of other case histories. This one is a East End parking garage. This project actually was in Sacramento, California, but went ahead and included it just because it's very similar. We see a lot of projects that look a lot like this one in the Dallas area and surrounding areas. This was a 6-story parking garage for the state of California Capitol Complex. Typical column loads of 835 kips, max column loads of 1,800 kips at the shear walls, with uplift loads of 660 kips. And this is just a slide I like to include. Sometimes there's a bit of a misnomer that geopiers can't be used to handle really heavy loads, and that's just not true. We support high rises, loads in excess of 2,000 kips all the time. It's not just slightly loaded structures that we can do, offer geopier support underneath. Another good project we did, Medical Center of Southeast Texas. This was in Port Arthur. It was a 260,000 square foot 5-story hospital. The footings were loaded up to 1,050 kips of compression, 1,080 kips of uplift. Of course, this is hurricane country here. Very soft to stiff clay over loose silty sand and stiff clay with a groundwater table at 16 foot. And the challenge was to control settlement in that compressive clay and loose sand while also providing uplift resistance for the wind loads at the shear walls. The solution was to utilize 1,230 Geopier elements, supported footings at 5,000 psf bearing pressure. We installed case piers up to 30 feet below grade on this job, and we concentrated piers at the shear walls where the loads were heaviest. We also utilized 40 kip uplift Geopier elements to handle the uplift loads. And in that picture there, you can actually see an uplift anchor. That's what that gentleman is handling there. And this is a picture of the finished Medical Center of Southeast Texas. It was completed in 2005, but this picture was actually taken after 2 hurricanes, Rita and Ike, and building's been performing excellent ever since. Here's a project, the Aloft Hotel. This was actually a Dallas project. This is on Mockingbird. This is a 30,000 square foot 6-story hotel. Column loads up to 780 kips. We were dealing with stiff to very stiff fat clay and sandy clay with medium dense sand and clay sand over shale and bedrock. The original design was for very deep drilled piers, and we came in and the geopiers were about 1/3 of that depth, and we were able to avoid the groundwater and just really help them avoid having to case drilled piers and have an expensive deep foundation option that's going to kind of be a detriment on their construction schedule. The challenge, of course, was to provide ground improvement in unique expansive soil conditions. So our solution was 245 Geopier elements. Shaft lengths range from 8 to 10 feet. We supported footings at 7,000 psf. We concentrated piers at the shear walls. And on this job, the swell was mitigated via remove and replace for the floor slabs only. So in closing, I want to leave you with a few red flags here, like, what's in it for me? What have you done for me lately type of a thing. When you're looking at geopiers versus undercut or remove and replace, think of this as a kind of point of no return. If you've got over X and replace of 5 to 8 feet or greater, give me a call, because we can oftentimes provide cost savings in these scenarios. And additional benefits, you can eliminate tiebacks and shoring requirements in confined areas and urban settings. We eliminate the dewatering needs for over X. We can reduce or eliminate spoils and the need for contaminated soil disposal using, the displacement systems discussed, like impact. And we can increase the design bearing pressure from, anywhere from 5 to 10 ksf. And that helps you, in your structural, shrink your footing sizes and maybe save on concrete costs. Another red flag here to remember, one of the red flags for deep foundations, if you're from an economic standpoint are looking at poor to marginal soils that are going to require, deep foundations up to 30 plus feet below existing grade, especially where there's a shallow groundwater table and you're going to have to case, keep us in mind. We can offer a high allowable bearing pressure, and we can control settlement, and oftentimes get it to where you don't have to be stuck using deep foundations and drilled piers. Additional benefits: we eliminate the use of the associated pile cap design. We can expedite foundation design and construction, reduce or eliminate spoils, and increase the design bearing pressure again. In closing, Geopier has a great track record, proven performance, over 10,000 successful projects, accelerated construction schedules. We can help you get the job done faster. It's a cost-effective solution. It's got design-build capabilities from start to finish service. It's green, sustainable systems. LEED. It's just aggregate. You put an aggregate back in the ground. Construction's clean. There's no mess to clean up. And there's, when you hear rammed aggregate piers, sometimes people get a little, they get a little nervous. But vibrations from our equipment is actually low. Peak particle velocities less than 2 inches per second. So don't be too put off by the name. We can eliminate dewatering, shoring, and other over-X and recompaction requirements. And that's the presentation. I appreciate everybody that listens to this, and if you have any projects you'd like to discuss with me, give me a call or give me an email. I'm available anytime, and I would love to help you fix some bad ground and save you and your clients some time and money on a project. Thank you.